So the last section of chapter 11 is relatively straightforward in the sense of it's deriving the suvat formulae, and it's unlikely you would be expected to use suvat formulae in any way in a variable acceleration question, but they may simply ask you to derive them. So it's useful for you to have a bit sort of under your belt using the relationship with variable acceleration to derive where the suvat formulae come from. Now, hopefully with your teacher, you derive the suvat formulae anyway, using displacement and velocity time graphs rather than using differentiation or integration like I'm going to do. But if not, doesn't matter. This is a way of doing it. So there's only one example, so it is just going to be a really short tutorial and then quite a lot of practice time. So a particle moves in a straight line with constant acceleration, a meters per second squared. So what I'm going to do to start with is draw an acceleration time graph. And if it moves in a straight line with constant acceleration, then it's going to look like that. Given that its initial velocity is u meters per second and its initial displacement is 0 meters, prove that A, its velocity, v meters per second at time t, is given by v equals u plus at, and its displacement, s meters at the time t, is given by s equals ut plus half at squared. So we'll do a part A first. Now, if this is an acceleration time graph, if I were to integrate acceleration, I get velocity. And that's because the area underneath an acceleration graph is velocity. So I'm going to integrate my constant acceleration, which is a. So because it's just a constant, it's just a number. So we're using obviously the letter a to represent that constant. And I'm going to integrate it with respect to t, because obviously my functions are in terms of time. So if I were to integrate that, it'd be at plus a constant c. Now, and this is equal to velocity in terms of time. What we do know, though, is that when t is equal to 0, velocity is equal to u, because the initial velocity is u. So u is equal to a times 0 plus c. Therefore, c must be equal to 0. Therefore, velocity is equal to, because you don't need the in terms of time because we know everything is in terms of time in this case, v is equal to u plus at, or at plus u, as required. Part B wants to demonstrate that displacement is s equals ut plus half at squared. Well, this time what I'm going to do is I'm going to do a velocity time graph, and I'm going to plot this line. So that would be u. So that is the line v equals u plus at. So obviously u is going to be its initial velocity, so it's where it starts, and it's increasing at a constant acceleration. So if I want displacement, I want the area underneath that graph. So displacement is the integral of velocity with respect to time. So it's the integral of u plus at with respect to time. So I'm going to integrate this in terms of t. So s is equal to ut plus at squared over 2 plus c. Now I know that the initial displacement is 0. So when t is 0, s is equal to 0. So therefore the plus c must be equal to 0. because this would be 0, this would be multiplied by 0, and this would be multiplied by 0. So it's plus c. So therefore the equation for displacement is ut plus half at squared. And it is as simple as that. So I'd say it's worth doing a little bit of practice in terms of probably the questions asking you to derive the other formulae. Otherwise, it's just going to be an opportunity to really secure your knowledge of the variable acceleration chapter, and then to fill out for me the variable acceleration Google forms, so that I can again give you some feedback on that. So yeah, email me, message me if you need any help, but otherwise, yeah, that's it.